All right, class. I hope all is going well with the missions conference and with school. And hopefully you had no issues with the first video. And hopefully homework went well as you worked on the odds. And so let's get into lesson 2.2. Now, the homework for this lesson will not be due until Monday of next week. All right, so this is due Monday of next week. Tomorrow in class, I will go back to the chapter review of chapter 1, and we will do a chapter review getting you ready for Friday's test. Okay, so this is 2.2, polynomial functions. Polynomial functions. So we have here the form, and it can confuse some students. I'm looking right here, right? A sub n to the x to the n plus a sub n minus 1, x to the n minus 1, and then it goes on, right? Minus 2, dot, 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 all the way down to a sub 1, x sub 1, a sub 0. All right, so let me just first off get you to understand. This n is the highest power of the polynomial. In this case, n is 5. And a sub n means the coefficient of the fifth power term. So the 7 would be a sub n, right? N is 5 for our example, and the 7 is the a sub n, the coefficient of the highest power term. Now, notice the next term, 4 is n minus 1, right? 5 minus 1. And so the negative 3 is the a sub n minus 1 or a sub 4. So again, the form is just giving you it for any given power. I mean, the lead term could be 12th power, and then 11th and 10th and 9th and 8th and 7th and 6th and all the way down, right? The lead could be a cubed, and it'd be x cubed and x squared and x to the first and then a number. So this last term is just simply a number, right? A constant. Just a number, a constant. And again, we never show, the x to the first power. That would usually just be x. But I put the 1 there just to emphasize, right? So the a's are the coefficients of the independent variable, and the n is the power, right? And so n is the highest power. And so let's write a little bit of that. So first off, n is a whole number. So if we're going to have a polynomial, we need whole numbers, no fractions there, right? Fractions are radicals, and so no fractions. N also is the degree of the polynomial. N is the degree of the polynomial. And a sub n is called the lead coefficient. The lead coefficient. All right, and it's off again. Oh, I hate that. All right, let me try that. So a sub n is the lead coefficient. All right, so again, we've got the example here. With our example, n equals 5, a sub n would be the 7, right? A sub n minus 1 would be the negative 3, right? Because this would be a sub 4, right? The coefficient of the x to the 4th powered. A sub n minus 2 would really be a sub 3, right? 5 minus 2 is 3, and therefore the answer would be 6, etc., 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 etc. Okay? So I hope the format isn't too confusing, and I hope that that's understandable. Let's make the example A. Let's go B here. So let me just give you a couple of aspects here. So when we're talking about linear, remember, linear are things that are lines, then it's going to be first degree. So the highest power is going to be to the first power, right? So it's going to be a first degree. And interesting thing here is you're going to have one solution, possibly one solution. Quadratic is going to be second degree. And you're going to have up to two answers, so less than or equal to two solutions for quadratic. Now, polynomials, I'm just going to say poly. There's all kinds of polynomials, right? So cubed, fourth power, fifth power, sixth power, seventh power, etc. are all polynomials. So let's do a polynomial cubed, right? Third power, right? So this is going to be third degree, and there's going to be less than or equal to three solutions. And if we had a polynomial of to the fourth power, then it's fourth degree and less than or equal to four solutions. So here's what I'm trying to say. You have as many solutions, up to as many solutions as the degree of the polynomial, and the degree of the polynomial is the highest degree term. Okay? All right. Let's take a look at example 1 here, and it asks us a question. State the degree and the leading coefficient of each polynomial function. If the function is not a polynomial function, explain why. Okay, so look at A. So looking at A, what degree is A? You got an answer? All right, you should have said third degree, right? Because of that 3. And therefore the lead coefficient is the coefficient of the x to the third power, and therefore the lead coefficient is 2. Okay, looking at B. First off, is B a polynomial function, yes or no? Well, we can't have negatives. If you go back up here, remember I said n is a whole number. And just to refresh your memory, the set of the whole numbers, and I should have said a whole number, but n does not equal 0. So actually, should have said the natural numbers would have been better. But, you know, the set of the whole numbers are 0, 1, 2, 3, ... right? Okay, so this one is not a polynomial, not a poly. Okay. All right, C. Now the square root is with the 2, not with the x, right? The x here is not under the radical sign. So that's okay. This is a polynomial. What's the degree? Well, it doesn't always go in order. It's the highest power, so it's a fourth degree, right? And what's the coefficient of the x to the fourth power term? All right, you thinking of something? Hey, by the way, I always tell my students, don't be a copier, be a thinker. Make sure when I ask a question, think of the answer. So what's the coefficient? What's the lead coefficient? It's a -1, right? A negative x to the fourth is like a -1 x to the fourth. All right, and then J, this whole thing, remember we talked about this yesterday, I believe. This is the exact same thing. It's to the 1/2 power. That's not a whole number. It's not a poly. Okay? So identifying polynomial functions. All right, how about some things we know about polynomial functions? So polynomial functions are continuous. So again, if you were to draw the function, you'd never have to lift your pen or pencil off the paper going from its lowest value to its highest value, or from left to right from the domain. So that means it's continuous for the domain equals all the real numbers. right? That's a symbol for all real numbers. Right, so continuous. The graph of any polynomial is a smooth curve. A smooth curve. Here, let's sketch y equals x cubed. So, give myself a Cartesian plane, and here's the graph of y equals x cubed. It's a smooth curve, right? So, you know, something like this, y equals x to the fourth, looks something like this, right? But it's a smooth curve, and it, again, it has all kinds of variations. But that's the idea. Smooth curve is what you want to understand. And then C is really important. And I'm going to go to red here, end behavior. We've talked about this in the last chapter. The end behavior of the lead term. That's the highest powered term, right? Is the end behavior. Is the end behavior of the polynomial. So the end behavior of the lead term is the end behavior of the polynomial. Okay, so let's write some things. Okay, so end behavior of p of x equals a sub n x to the n. So this is called the lead term test, okay? And remember, n is just the highest power, and a sub n means the coefficient of the variable of the highest power. So we can write some things here. All right, so if we're going to understand some things, we're going to do a couple things here. I'm going to do my A in blue, and I'm going to use some color here. All right, so let's suppose we have a positive lead coefficient, so positive A, and we've got an X, and then the value of n is an odd number, right? A 1, 3, 5, 7, 9, 11, etc., 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 etc. Okay, and you got to be careful here. The positive A is the way it ends, or the right side. So the right ends positive. So right is up. The fact that this is odd says the left, or the beginning, is opposite. So if I were saying it in words, I know that this function ends up, but it starts off opposite, so it must start off down. So this is a down, up. Now, remember, down means it's coming from negative infinity, and up means it's going to infinity. And that's really the way we term it. We don't really say down, up, though thinking down, up is a little bit easier. But negative infinity, so it comes from negative infinity, from down, and ends up to the right as you move left to right to positive infinity. So, you know, for example, if we had y equals 4x to the fifth minus 6x to the fourth, and I'll say etc. You know, you can have a cube and a squared in the first power, etc., 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 etc. This is going to say that we're going to end on the right, up, and this is odd, so the first one, the left, is going to be opposite, right? So that's every time, every polynomial. Okay, what's another possibility? Positive a and an even exponent. Positive a even exponent. Well, again, you got to start with the lead coefficient, but it's going to tell you the right side. So the right is going to be up. So again, I'm going to come over here, and on the right one, I'm going to put the up, right? And I'm going to show you the right way this time, but the thinking up above. And then the even tells you it's the same. So how does it start? How is the left? So the left is also up or infinity. So it's an up, up, and away in a beautiful balloon. All right? Third possibility. Now we got a negative a, x, and we'll go back to odd again. So negative a and an odd exponent. Okay, the negative a says the right is going to be down. So now our right is negative infinity, right? The odd says the left is opposite. What's the opposite of down? It's up, so it's infinity. So this is infinity, negative infinity. Let me show you an example. If we had y equals negative x cubed, this thing is going to come from positive infinity and end up at negative infinity. Right? Because the lead coefficient was a -1 and the exponent was odd. And then the last possibility is a negative a with an even exponent. Once you learn the pattern, it's pretty simplistic. So again, always start with the lead coefficient. Always understand you're starting with the right. And so our right is down. Our right is negative infinity. Even says the left is the same. So this one is negative infinity, negative infinity. And that's the lead term. Okay? Now, let me just mention your book is going to use limit notation. Limit notation. They're not going to say left and they're not going to say right. So let me just be clear. Here's how, let's see, find a place to put this. Here's how they would say left. They would say left as the limit of p of x, polynomial, as x approaches negative infinity. That's what they mean by left, right? And they'll mean right by saying the limit of the function p of x as x approaches infinity, which is positive infinity. So just be careful. That's the notation the book likes to use. That is, you'll see that notation more and more as you get into calculus. But again, to understand left and right is a whole lot easier to understand than the limit of p of x as x approaches negative infinity. Again, left side, right side. What's happening on the left, what's happening on the right. Okay, let's take a look at a couple examples here. So describe the end behavior of each polynomial function. Okay, so we want to be able to describe the end behavior. So remember, we are looking at the lead coefficient. That's the a value, right? So remember, the -2 is the right-hand side, and negative is down. So what's the right going to be? -infinity. The power, the degree, is odd. Odd means the left is going to be opposite. So if the right is down, the left has to be up, and that's positive infinity. So infinity, comma, negative infinity. Let me see if that's how they termed. Okay, see, they used limit notation. So again, as I showed you a minute ago, that's the notation they used for the left. Notice they got infinity. And this is the notation they used for the right. And notice they got negative infinity. Okay? They also described this as an odd function. So, but no worries there. Okay. So, and check. Here's the graph of that, by the way. And notice the left end is indeed infinity, and the right end is indeed negative infinity. Okay, be careful with B. Take a look at B. Can you describe the end behavior? So again, I like the interval notation. But again, it means the exact same thing when you're saying the limits. Okay? So how would you say it? Go ahead and do it. Do B. Do B. Okay, I hope you determined that the a is a positive 1, and therefore the right side is going to be up, or infinity. Remember, you got to look at the highest power term. It may not be in the proper order, and this one wasn't. And even means they're the same, so infinity, infinity. And sure enough, when you take a look at the example, we see that this thing on the left is infinity, and on the right it is infinity. Okay? Now, look at this last example here. Is the power of this going to be even or odd? It's the power. Well, because it's opposite, it's got to be an odd power. Now, let me show you one other interesting thing. Watch how many direction changes we have. We're going up, we're going down, we're going up, we're going down, we're going up. This power has to be greater than or equal to 5. It's got to be at least a 5th degree. It might be more, we're not sure. It might be more, but it's at least 5 because there are 5 directional changes. Now, you don't always see a directional change, but because they're subtle, and so we know it's at least 5. So this is greater than or equal to 5. Okay. How about zeros and relative extrema? All right, so the term relative extrema is important in calculus. Again, we're pre-calculus, so we want to get this term down, relative extrema. So zeros and relative extrema. So let's write some notes. A. If p of x, some polynomial function, equals 0, and x equals 0, I'm sorry, my bad, and x equals c, I'm going to put that in red. All right, so we got a polynomial function. The function is set equal to 0, and the x value is c. Then x equals c is a solution. So you got some polynomial that equals 0 and x equals c is a solution, then x minus, use your color here and do a red C again, x minus c is a factor. Oops, excuse me, let me go back here, is a factor of the polynomial, of the poly, and red C again, C is a 0 of P of X. Okay, that's a lot of words. That's a lot of words, and I don't want to confuse you with a lot of words. I'll give you an example of this in a minute. Here, let me just show you. I'll show it to you in a minute, right? We'll get there. So that's pretty straightforward. Okay. So it's just a way of the 0 comes from the factor. So if you got a 0, then you've got a factor. If you got a factor, then you got a 0. That's all it's saying. And again, I'll show you an example in a minute. A polynomial, poly, of degree, and I'm going to go red for degree, of degree n. A polynomial of degree n has, and I'm going to go red again, at most n, and then go to green, real number zeros. Okay, I've got a little bit more to write, but let me pause there. So here's what we're saying. A second degree polynomial, right, a 2, has at most 2 zeros. A third degree cubed has at most 3 zeros. Right? A fourth degree has at most 4 zeros, right? A first degree has at most 1 zero, etc., etc., etc. Okay, so that's the 0 part. Let's get to the relative extrema. And go to red here, at most, and at most, and I'm going to use blue here, n minus 1, back to red, relative extrema. And you say, I don't even know what a relative extrema is. Yeah, I know. I'm going to show you in a minute. So hang in there. I'm going to show you. But here's the thing, right? If you got a third degree, there's at most 2 relative extrema. If you have a second degree, there's at most 1. Might be none, but there is at most 1. If you have a first degree, you have no possible relative extrema. 8th degree, you could have 7 relative extrema. So, all right, you're probably going crazy. Here, let me go back a moment. You can go back in your notes and see this example right here. Let me show you the extrema. It's the places where the curve changes directions. So we went from going up to going down. There's a relative extrema. Here we went from going down to going up, a second relative extrema. Here we went from going up to going down, a third relative extrema. Here we went from going down to going up, a fourth relative extrema. So they're the points of the function where we go, where we change directions, okay? And so this was a, by the way, we thought this was a 5th power, maybe more. And so we could only have at most 4 if it's 5th power. If it was 7, we could have at most 6, but we may not have 6. We may only have 4, etc., 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 etc. Okay, and here's the thing. When you get to calculus, we'll be able to find the values of those relative extrema. We'll be able to find the values of those max and mins. And I'm going to put that in right here. Relative extrema is max or mins, right? Maximums or minimums. The places where the curve changes direction. Okay, C. Let's do an example. Let's suppose we have P of x equals 3x to the 5th minus 6x to the 4th. Okay, before we do anything, let's figure out the end behavior. So remember, end behavior, we look at the lead coefficient first. It's positive. So we're going to end up to the right going positive or up, positive infinity. Now to get the left, look at the exponent. It's an odd exponent, a 5. So it's going to be opposite. So we know we're negative infinity, infinity on our end behavior, right? We are a down, up. Now, let's set the function equal to 0. We're going to be able to find the zeros. So we set the function equal to 0. All right, to solve this, we can factor out a 3x to the 4th. Right? We factor out a 3x. Oops, that is a 2. Whoops. Did you drink the Kool-Aid? Say, no, I barely had time to write it. Yeah, I know. That happens. It's math. Okay. When you set this equal to 0, you get x equals 0. When you set this equal to 0, you get x equal 2. Okay, let me go back to the opening line and make a connection. Do you see up here where we said x equals c? You see here where x equal 2? Then we said there must have been a factor of x minus c. See how there was a factor of x minus 2? That's all we're saying. That's all we're saying. Here, let me give you one more quick example. If I had 0 equals x plus 1 times x minus 2, my zeros are negative 1 and 2. Therefore, I know I had those factors. Or let's say it this way. Let's suppose I had an example where my zeros were 3 and 5. Well, I know this must have been an x minus 3 times an x minus 5 to give me those zeros. That's all that first part is saying, okay? But that's important. It is important. Okay, D. D. If P of x can be completely factored, and completely is important, if P of x can be completely factored, if P of x can be completely factored, okay, what if when it's completely factored, there is a repeated factor, and we'll call it x minus c, and because it's repeated, we'll use m for the repetition, right? Like maybe there's 2 of the same factor, or 3 of the same factor, or 4 of the same factor, etc., etc. Then what we have is, that should have just been blue, C, right, red, sorry, is a repeated 0. C is a repeated 0. Okay? And look, the example for this would be, what if you factored something and it came up x negative 2, x negative 2, right? Well, there's only one 0. It's x equal 2. We don't say 2 twice. 2 is 2. It can't cross itself in the same place. It's just x equal 2. Okay? So it's a repeated 0. And so m represents the repetitions. So now we have some possibilities. Okay? If m is odd, I'm going to do m in green. So what if m is odd? If m is odd, the graph must cross the axis. So the graph crosses the x-axis. At C, it has to. There's no other way. I mean, but because it's a 0, it's got to cross. But what if m is even? Then the graph touches the x-axis at C. It touches the x-axis at C, right? Which is technically C0, right? Because the thing set equal to 0. And so touches means it doesn't cross. You might say, well, how does that here? Let me show you. Just quick idea. If this parabola has a vertex right there, it touches at C, but doesn't cross. So the change of direction happens at the x-axis, and therefore it doesn't cross. What does that result in? And is an extrema. Right? So whenever you have multiple of the same factor and the exponent is even, 2 of them, then it crosses right at it. Matter of fact, you know, this one would look something like this, right? Where the vertex is at 2, right? Does that make sense? All right, got one more thing. I got 8 minutes, so I think I'm in decent shape. I wish I had time to do number 4. If you look in your book, it's there. And it's an important one because it's going to show you real zeros and relative extrema. So please take some time and do that. Use Desmos and show them. You know, example 5 again shows you an interesting one. And notice here is a 0. Must have been a single factor because it crosses. Here is a 0. Must have been a single factor because it crosses. Here's an extrema at the x-axis that must have been more than one of the same factor to produce that. All right, and so that's kind of interesting aspect there. I think that's the case. Okay, so here it is. It's an x squared. So there's 2 of them, and even power it touches. Doesn't cross. Okay, here's the 1 0 and here's the other 0. All right, makes sense? And you can do the M behavior and all of that and look at all of that as you have time. Okay, let's get to the last thing, the intermediate value theorem. So this is functions cross the x-axis. So what we're dealing with is functions crossing the x-axis between A and B. And so the way that they say between A and B is they say bracket A, comma, bracket B, but what they mean is between A and B. So, you know, don't get that confused. And so intermediate. All right. So we got a couple possibilities. If continuous, no jumps, right? No point discontinuities. If continuous over the AB, and this is the domain. If continuous over B, and there exists, by the way, a backwards E is a quick way of saying there exists, a value of N between A and B. Then C exists. Let me stay and go back to blue. Then C exists. So there's some C in between. All right. Now, I need to clarify a few things here. We're going to make our A a negative value and make our B a positive value, right? So if it's continuous over going from negative to positive, or going from positive to negative, right? All this is a complicated way of saying we're crossing the x-axis. That's all sometimes we can take things and make them complex. Let me show you. If A is here and B is here, right? If A is there and B is there, if the A value is negative, let's say it's here, and the B value, I'm sorry, put it in the wrong place. If the A value is negative and the B value is positive, then this thing must have crossed the x-axis. I mean, that's all we're saying. So please, don't try to make this confusing. Let me try to make it easy for you with an example. All right, we'll end up here. Let's suppose we have a function, a polynomial p of x, and it equals negative 4x cubed plus 3x squared plus 5x minus 3. Okay. What we want to do is we want to find the relative extrema. So we want to find extrema. And so we need to deal with the scenario here, right? So, okay, so to figure this thing out, what I want to do is I want to do an XY chart, but I'm going to do it sideways. Okay? And I need to come up with some values here. And so I'm going to start off with a negative 3. And I could have gone further, negative 4, negative 5. And you just got to kind of use some common sense here. But look what happens. When I put in negative 3, I output 72. Okay, notice I outputted a positive value. When I try negative 2, I output a 31. Okay, I'm also still a positive value. When I input a negative 1, I output a negative 1, a negative power. Up, ding, 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 ding. Notice I went from going up to going down. Went from positive to negative. I had to have crossed the x-axis. I must have. So, I know this. I know I have a 0, right, between negative 2 and negative 1. There's a 0 in that interval. Because from negative 2 to negative 1, I went from positive to negative. All right, I'm going to keep going. How about 0? When I input 0, I output -3. Okay, no change. I'm still negative. When I input a 1, I output a 1. Ding, 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 ding. There's another change. I was going down, now I'm going up. So again, I cross here. Got another 0 between 0 and 1. A is 0, B is 1, right? That's where the A and B is. That's all. Okay, and let's keep going. Let's do a 2. 2 gives me a -13. Up, I'm going down. Ding, 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 ding. I cross again, right? I was going up, I'm going down. So between 1 and 2. And if I do a 3, I'm way up. I'm way down to -69. I'm continuing down. Okay, I have 3 zeros between -2 and -1, between 0 and 1, and between 1 and 2. And put this in Desmos, and you'll see that. All right, if you put it in Desmos, you will see it, and it makes it very interesting. All right, I'm out of time. So remember, this homework is due Monday. Chapter review tomorrow. So I want you to do 1, no original for 3 and 4, 6 through 9, 11, then go back and get 10. Do 15, go back and get 14, 19, 21, 23. All right, hope you guys do well. See you tomorrow. I'll have a chapter review for you and then test on Friday. All right, have a great day. Okay, so back here for just a second, I want to show you the function here. I did it in Desmos. So notice between -2 and -1, there's the 0. Second one, notice between 0 and 1, there's the 0. And notice the third, between 1 and 2, there's that 0. So just as we predicted, zeros between -2 and -1, between 0 and 1, between 1 and 2. So that's what you want to pay attention to with the intermediate value theorem. We're trying to find intervals where the function changes from going up to going down or going down to going up, and you can do it with an XY chart. Okay, hope you have a great day.